Welcome, guys. In this video, we are going to study two quite useful theorems in calculus, Rolle's theorem and mean value theorem. Let's take a look at the following Rolle's theorem. First, let function f be continuous on closed interval from a to b and differentiable on the open interval from a to b. If function has zero value at those 2 points, then there is at least one point c in the interval from a to b or in open interval from a to b such that it has stationary point at point C. The proof of that theorem is pretty straightforward. It's similar to the proof of extreme value theorem. So let's assume that we have a function and we're looking at it on closed interval from a to b. It has zero values at points a to b. Then in case if function is constant, then this is pretty simple case. If it has zero value on whole interval from a to b, then all these points are stationary points inside of this closed interval from a to b. Now let's assume that function isn't constant on the whole interval. Then let's assume that it is increasing. It's starting at point A. Then similar to the proof of extreme value theorem, for this function to reach point B, then it should switch from being increasing to being decreasing at some point on that interval. And at that point, since our function is continuous and differentiable, then this point is going to be a stationary point. So derivative of that function at point C is going to be equal to 0. Let's take a look at the following problem. Let's find the two x-intercepts of the function x squared minus 5x plus 4 and confirm that we have stationary point at point C between those two intercepts. So we can express f of x as x minus 1, x plus x minus 4. So we have two intercepts at 1 and 4. So these two are here. Now let's show that we have some stationary point in between those points 1 and 4. First of all, let's confirm conditions required for Rolle's theorem. First of all, our function needs to be continuous on closed interval from 1 to 4. So this is polynomial, it is continuous everywhere. Next, we need to confirm that it is differentiable on open interval from 1 to 4. This condition is also satisfied. We know polynomials are differentiable everywhere, meaning that now we can apply Rolle's theorem. Since our function has zero values at 2 points 1 and 4, then it means that in interval from 1 to 4, there is at least one point such that the value of derivative of function is equal to 0. So we have stationary point in that interval. So that point corresponds to a point 2.5. Let's confirm that by finding derivative and equating it to 0. So first derivative of f of x is equal to 2x minus 5. So equating it to 0, we have x that is equal to 2.5. So at point 2.5, we have stationary point indeed. Now, those two conditions that we need for Rolle's theorem, the conditions that function needs to be continuous on closed interval and differentiable on open interval from a to b are necessary. Let's take a look what's going to happen if one of those two conditions is omitted. So in this case, we have function y is equal to absolute value of x minus 1. And we see that it has zero values at points minus 1 and 1. So we assume that then, according to Rolle's theorem, that our function needs to have a stationary point on open interval from minus 1 to 1, which is not true in this case, since there are no stationary points, as we can see from the graph. The reason is following: we cannot apply Rolle's theorem here because our function is not differentiable at all points on open interval from minus 1 to 1. Our function is not differentiable at point minus 1. At point 0, at point x is equal to 0, our function is not differentiable. Okay, also Rolle's theorem states that there is at least one stationary point on that open interval. There might be several stationary points, as we can observe in the following case. On the interval from 0 to 2 pi, this function y is equal to sine of x has two stationary points, at pi over 2 and 3 pi over 2. So we can have several stationary points in between of zero values of our function. It should be noted that Rolle's theorem is a special case of more general result known as mean value theorem. Mean value theorem states the following simple geometrical fact. If we have function that is continuous and differentiable on interval from a to b, continuous on closed, differentiable on open interval, then there is at least one point C in that open interval from A to B such that the slope of tangent line at that point is parallel to the slope of a second line joining points A and B. So mathematically speaking, it means that there is at least one point C in open interval from A to B such that f prime at point C is equal to the slope of tangent line, and slope of tangent line is equal to the tangent of that angle, which is equal to f at B minus f at A divided over the length of this interval over B minus A. And we might have a case when there are several points such that the slopes of tangent lines are parallel to the slope of secant line, like in this graph over here. So mean value theorem, let function f be continuous on the closed interval ab and differentiable on the open interval from a to b. Then there is at least one point C in AB, open interval AB, such that f prime at C is equal to f at B minus f at A over B minus A. The proof here is straightforward. Since we already proved Rolle's theorem, we can use it in this proof here. If we denote the following function as a distance function, so this is distance function between the second line and the graph of function, so it is equal to the difference of values of our function f of x minus this equation for secant line. Then we can see that graph of f of x intersects secant line at a and b, meaning that this distance function is going to be equal to 0 at those 2 points. And since it's continuous and differentiable, we can apply Rolle's theorem and show that there is at least one point such that there is going to be a stationary point for distance function, meaning that there is at least one point C such that V prime at C is equal to 0. And then if you decompose V prime at C is equal to 0, you'll get the following expression here. Let's take a look at the following problem and let's try to solve it using mean value theorem. Shows that the function 1 over 4x cubed plus 1 satisfies the hypothesis of mean value theorem over the interval from 0 to 2, and find all values of C in the open interval from 0 to 2 at which the tangent line to the graph of f is parallel to the secant line joining the points 0, f at 0, and 2, and f at 2. So first of all, let's try to find the slope of secant line joining these 2 points. So the slope of secant line is then equal to f at 2 minus f at 0 and divided over 2 minus 0. The value of function at point 2 is equal to 2. At point 0 it is equal, at point 2 it is equal to 2 plus 1. At 0 it is equal to 1. So minus 1 divided over 2, it is equal to 1. So the slope of secant line is equal to 1, and we need to find a point in that open interval from 0 to 2 such that f prime at C is equal to 2. C is equal to 1, so we need to find such point C such that f prime at C is equal to 1. So first, let's find the derivative of our function. The derivative of our function is then given as 3 over 4 x squared. We equate it to 1. So solution to that is x is equal to plus minus root of 4 over 3. The point that is positive and inside of our open interval is then point x is equal to 2 over root of 3. And this point is an interval from 0 to 2, and somewhere here we can see that the slope of tangent line at that point is equal to the slope of secant line joining points 0, 1 and 2, 3. Mean value theorem has also nice velocity interpretation. If we consider this function f as a function of position against time, so let's call it s of t, then this fraction here might be represented as position at time t2 minus position at time t1 divided over t2 minus t1, which represents average velocity of a point, let's say, on time interval from t1 to t2. Now, from basic physics, we know that instantaneous velocity, let's call it v inst, which is a function of time, is represented by the first derivative of position function. Then we can see that here at the left side we have, according to mean value theorem, at the left side we have s prime of t, and on the right side we have this function here, which represents average velocity. So basically, mean value theorem states that if on time interval from t2 t1 there is at least one point such that an instantaneous velocity of a point is equal to the average velocity on the of the point on the interval from t1 to t2, and it's quite useful property. Let's take a look at the following example. You are driving on a straight highway on which the speed limit is 55 miles per hour. At 8:05 a.m., a police car clocks your velocity at 50 miles per hour, and at 8:10 a.m., a second police car posted 5 miles down the road clocks your velocity at 55 miles per hour. So you are smart enough, so you are slowing down before the police cars. Explain why the police have a right to charge you with a speeding violation. So the speed limit here is 55 miles an hour. We have to show that there was at least one moment of time where your instantaneous velocity, the speed shown on your speedometer, was above 55 miles per hour. So let's measure your average velocity on that time interval from 8:05 to 8:10. So so we can also represent this as delta S over delta T. So delta T was equal to 5 minutes. 5 minutes is 1/12 of an hour. Now, the distance that you have traveled, so second police car is posted 5 miles down, so the distance that you have traveled was 5 miles. So your average velocity was equal to 60 miles per hour, meaning that according to mean value theorem, your instantaneous velocity during the time interval from 8:05 to 8:10 a.m. was at least 60 miles per hour at least once, meaning that they have a right to charge you with a speeding violation. All right, guys, that concludes our video on mean value theorem. Thank you for watching.